As chair of the computer science department, one of the big challenges in my job each semester is building the class schedule for the department. Often, students ask why I haven't built a piece of software to automate this, but it's a surprisingly difficult task to code. There's always some compromise in the schedule, because there are many factors to consider, and some of them are competing. Each faculty member has a set of classes he would like to teach, but those selections often overlap and rarely cover all of the necessary courses. Some classes require particular classrooms, and the faculty have preferences on rooms and times that may also be conflicting. Finally, some pairs of classes cannot be scheduled at the same time because students are required to take both of them in the same semester. Building the schedule is a good example of the set of problems called optimization problems. In these problems, there is no perfect solution, or finding the perfect solution would take more time than we have. Instead, we're trying to find a solution that maximizes some particular value. In the case of the schedule, we're trying to maximize the extent to which the schedule matches the faculty requests while meeting the requirements of the semester. Another example of an optimization problem is path planning. Consider what you would do if you were planning a trip from New York to San Francisco. If you didn't have any stops planned along the way, there are a great many paths that you could take. In general, you'd plan a path that stayed on big highways and was as straight as you could find. When you're finished, you aren't sure that you've picked the absolute shortest or quickest path, but you are sure that it's good enough. Finding the perfect answer in an optimization problem is usually impossible because there are so many possibilities to be considered. In our scheduling problem, we might have to consider every possible combination of room, time, and faculty member for all of the courses. For planning our trip, we might have to look at every possible route between our starting point and our destination. The sheer number of solutions makes looking at each solution impossible. For computer scientists, optimization problems are characterized by the idea that, since we can't compute the perfect solution, we need a way to find a solution that is always good enough.
Genetic search is a strategy that we use for optimization problems that is based on the concept of genetics in biology. The basic idea behind this strategy is to randomly generate a set of individuals that represent solutions to the problem. Then, for a number of generations, use the current individuals to breed a new generation of individuals. If we are careful about which individuals breed and define how they breed so that their offspring are likely to represent better solutions, then after a large number of generations, our best individual will be a solution that is good enough. Let's look at an example to try to clarify the strategy behind genetic search. Suppose we wanted to generate the string, "Hello World." I know we could easily generate that directly, and this isn't an optimization problem at all. So just go with me for now, and we'll generalize this to more interesting problems in just a minute. Since we are interested in generating a particular string, the individuals in our population will initially be randomly generated strings. With each generation, we compute how good a solution each individual is. In this case, that means that we measure how close each string is to the string, "Hello World." We throw away the worst individuals and then use the ones that are left to create more individuals. These new individuals are usually a combination of two good individuals. For example, we might take the first few letters from one individual and the rest of the letters from another individual. In addition, every now and then we randomly cause a mutation in an individual. This might mean inserting or deleting a letter or making one letter change its value slightly. For example, we might choose to change an M to be an N. We'll talk more about breeding strategies a little later. Over many generations, because we keep and breed the individuals that represent the best solutions and throw away the individuals that represent the worst solutions, the best solution in the population approaches an optimal solution. In other words, that best solution is good enough, even if it isn't optimal.
In each generation, the algorithm measures how closely the solution each individual represents matches the optimal solution. This is called the algorithm's fitness. As an example, let's think about the Hello World problem. In measuring the fitness of an individual solution, we want to account for two things. How close is the individual string to being the correct length, and how wrong is each individual character? We would also like to make sure that as the strings get closer to Hello World, the fitness measure increases. Good fitness has higher values than bad fitness. We can consider the two parts of fitness separately and sum their measure to create an overall fitness score. The fitness of the length of a string can be measured with 11 minus the absolute value of 11 minus L, where L is the length of the individual string. If the string has the correct length, this will give a fitness of 11, the number of characters in Hello World. When the string is too long or too short, the fitness of its length will go down. Now we need a measure of how close each character is to the character it needs to be. For example, if the first character in our individual is F, then it is 2 away from the H that we need it to be. The computer makes it really easy to calculate these differences because it actually stores the characters as numbers. The Unicode standard maps numbers to characters, so while they look like characters when they are displayed, they are really stored as numbers. For example, our H is stored as 72 and F is stored as 70. Since Unicode maps the letters to sequential numbers, we can tell how wrong a character is by subtracting it from the character it should be in the optimal solution. The absolute value of H minus F equals 2. Since our second fitness measure wants to account for how correct each character is, we can subtract each character from the character it should be in the optimal solution and sum those differences across all of the characters. However, that sum will increase when the string is bad, and we want fitness to be large when the string is good. Therefore, our fitness measure will take the reciprocal of 1 more than that sum to prevent dividing by 0. Our overall fitness will be a sum of both of these fitness measures so that both the length and the accuracy of the letters affect the fitness of a string.
We've shown a fitness measure for our example problem, but let's talk about fitness in the context of some real optimization problems. Remember the problem of computing a path from New York to San Francisco? If we wanted the shortest route, then the fitness of an individual route could be the reciprocal of its length. As route gets shorter, that measure grows, which is exactly what we want from a fitness measure. However, if we were searching for the quickest route, then we'd have to estimate the time it would take to drive the route, accounting for speed limits, and take the reciprocal of that measure. Notice that we design the fitness measure based on the type of solution we're looking for. The problem of scheduling courses does not have a straightforward fitness computation. We may want to optimize from different perspectives. We could measure how close each faculty member's schedule is to what they requested. In this case, fitness would incorporate whether they were assigned the courses they wanted and how close to the day and time assignments they requested. We could also measure fitness from the students' perspective. Since we know which courses are likely to have the same students, we could try to put those courses closer together so that student schedules would not have short open times. From another perspective, the university may want to optimize the use of the rooms, so we could measure the number of rooms the schedule required and try to minimize it. In reality, the true fitness of the solution would be some combination of these factors. Clearly, as the problem becomes more interesting, the computer scientist is going to have to be creative in the definition of the fitness measure. This is particularly true because the fitness is going to define the individuals that the algorithm is going to find.
At first glance, it seems that at each generation we should let individuals with the best fitness breed to make the next generation, and in general this is true. However, individuals whose overall fitness is not good may have some important individual characteristics that would benefit the next generation. For example, a route on our trip may be very long because it goes through Florida, but it might have a short path through Oklahoma that none of our shorter routes have found. Therefore, we'd like everyone to have some chance of breeding, but we'd like individuals with better fitness to have a greater probability of breeding than individuals with lower fitness. One strategy for selecting individuals to breed is called roulette wheel selection. Picture the roulette wheel at a casino. Every time it is spun, the probability of it stopping at each number is the same. In other words, we don't know where it will stop, and each stop position is equally likely to happen. Suppose we spun the wheel to select an individual for breeding. If each stop on the wheel selected one individual, then each individual would have the same probability of breeding. That's not what we want. Now picture a pie chart, where the portion of the pie chart given to each individual reflects the fitness of that individual. Individuals with better fitness will take up larger portions of the pie chart. If we lay that pie chart on our roulette wheel, then the number of stops on the wheel associated with each individual will be proportional to the individual's fitness. This means that when we spin the wheel, individuals with better fitness are more likely to be selected. We set the scale of the pie chart so that every individual has at least one position on the wheel, and therefore has some chance of breeding. Obviously, the algorithms in a computer aren't actually spinning a roulette wheel. The actual implementation involves generating random numbers and proportional fitness measures, but the analogy to the roulette wheel describes how the algorithm is designed quite well.
Once we have selected the individuals that we are going to breed, we have to decide how we are going to create a new individual from them. The standard method for this is called crossover. To create the children, we select a random place to split the parents. Then we take the first part of one parent and the second part of the other to build one child and use the remaining parts to build the second child. In many situations, the standard crossover method results in children that aren't correct solutions to the problem. For example, think about our trip planning problem. The parents are two different paths. At the end of 10 legs of the trip, one parent could be in Ohio while the other is in West Virginia. If we split at the point for crossover, the children wouldn't be connected path. For this situation, we'd have to find some intermediate stop that was in both parents and split the routes at the point and then use the crossover to create the children. Often situations require more creative breeding strategies than simple crossover.
While the strategy behind genetic search is well understood, applying it to a particular problem often requires a great deal of creativity. First, finding the way to encode a solution in each individual can be a challenge. We need a way to encode a solution so that crossovers and mutations produce offspring that are valid solutions to the problem, and it is not always obvious how to do that. Then we need to define the crossover and mutation operations that make sense. While we might use the strict crossover and mutation operations, in most situations they result in offspring that are not valid solutions to the problem. Instead, we usually have to define some problem-specific operations. We also need to define a way of computing the fitness of an individual. This is the characteristics that the algorithm will optimize, so we have to be sure that we're really measuring the aspects of the solution that we care about. There are lots of parameters to the algorithm that we have to tune. The size of our population, the number of individuals who survive from one generation to the next, the rate of mutation, and the number of generations we compute before selecting the best individuals as our solution. Each of these can make the algorithm find better or worse solutions. Often, it feels like building a genetic solution to a particular problem is an optimization problem itself. Long after we have finished building the code, we are playing with these parameters, studying how they affect the types and quality of solutions the algorithm finds.
Genetic search is a good example of the kinds of things computer science students study. It's a problem-solving strategy that can be used in a variety of situations. But each time you use it, you have to analyze your situation and bend the strategy to fit that situation. Every time you use it is different, and getting good results from it requires a thorough understanding of the problem you're trying to solve and an understanding of what makes a solution a good solution. Anybody can code a solution that seems to work, but good computer scientists build systems that produce good solutions every time. We've built a new website that we're hoping will build a community around these podcasts. There's space for comments and discussions associated with every podcast, and we're really hoping that you'll join in. Check it out at webspace.ship.edu/wix. We also want to send a shout out to the Mac OSG podcast for all of their support. We certainly like Macs, and their podcast is always fun and interesting. Check it out.